Scene script, have you ever stopped to ponder what makes up everything around us? Let's embark on a journey to the heart of matter, where the building blocks of everything we know reside, the realm of atoms. Atoms are fascinating entities. They're the smallest unit of any element that retains the properties of that element. Picture this. Every object you see, every texture you feel, every aroma you smell, and every flavor you taste is a complex orchestra of atoms. Yes, you heard it right. Everything we encounter in our daily lives is made up of these tiny, almost invisible particles. Now, the concept of atoms isn't as new as you might think. In fact, it dates back to ancient Greece. The philosophers of that time were quite the deep thinkers. They pondered the nature of matter, asking questions like, what is the world made of? And how small can something be before it's no longer the thing it was? And from this philosophical musing, the concept of the atom was born. The word atom itself originates from the ancient Greek word atomos, which means indivisible. This comes from the Greek belief that if you were to keep dividing matter, there would eventually be a point where you couldn't divide it any further. That smallest, indivisible piece of matter was what they called an atom. But hold on to your hats, because the story of atoms gets even more intriguing. As we ventured further into the atomic world, we discovered that these atoms, these so-called indivisible particles, aren't quite as indivisible as the Greeks once believed. In fact, they're made up of even smaller particles. But as we'll see, atoms aren't as indivisible as the Greeks once believed. So buckle up, because we're about to dive deeper into the atomic world, and trust me, it's a journey you don't want to miss. At the heart of every atom, there's a tiny nucleus, a bustling city of particles. Now, let's dive into this city and meet its inhabitants, the protons and neutrons. These two are the primary constituents of the atomic nucleus. They are like the mayor and city council, the key decision makers of the atomic city. Protons are the positively charged particles in this mix. They're like the extroverted, outgoing members of the community, always attracting attention with their positive energy. Their role is crucial because they determine the identity of the element. Think of it like this. The number of protons in an atom is like the zip code of a city. Just as a city's zip code tells you where it's located, the number of protons tells us what element the atom is. On the other hand, we've got neutrons. They are the neutral particles with no charge at all. They're the introverts of the nucleus, neither attracting nor repelling other particles. Despite their lack of charge, they play a crucial role in stabilizing the nucleus. You can think of neutrons as the city's infrastructure, the bridges and roads that keep the city together. Without them, the city, or in this case the nucleus, would fall apart. So, in the hustle and bustle of the atomic city, protons and neutrons work together to keep things running smoothly. They're the heart and soul of the atom, the engine that powers everything else. Their positive and neutral charges balance each other out, creating a stable environment for the rest of the atom. In summary, protons and neutrons are not just particles. They're the life force of the atom, the key players in the grand scheme of atomic structure. They determine the identity of the element and ensure the stability of the nucleus. So the nucleus is like the city center, bustling with energy, but what about the outskirts? Around the nucleus in the suburbs of the atom, we find the electrons. These tiny particles are always on the move, like commuters in a bustling city. They have a negative charge and orbit the nucleus in a series of shells or energy levels, each one further from the core than the last. Electrons are not just aimless wanderers, though. They have a vital role to play in the grand scheme of atomic life. You see, it's the electrons that get involved in chemical reactions. They're the social butterflies of the atom, always ready to mingle with their counterparts in other atoms. When an atom wants to bond with another, it's the electrons that make the introductions, swapping and sharing to create the bonds that hold molecules together. Now you might be wondering, why are electrons so important? Well, think of a city without its suburbs. It would be incomplete, wouldn't it? The same goes for an atom without its electrons. They aren't just there for the ride, they're essential for the functioning of the whole. For instance, consider the role of electrons in electricity. When a voltage is applied to a piece of metal, it's the electrons that start moving, creating an electric current. And it's this flow of electrons that powers our homes, our gadgets, and our lives. But even though electrons are always on the move, they never stray too far from the nucleus. It's as if an invisible force is keeping them tethered, just like the gravitational pull of the Earth keeps the moon in orbit. This force is the electromagnetic attraction between the positively charged nucleus and the negatively charged electrons. So in essence, electrons are more than just inhabitants of the atom's outskirts. They're the lifeblood of the atom, the movers and shakers that keep the atomic world spinning. Without them, the atom and indeed our world would be a very different place. So electrons are like the satellite towns around the city, essential for the functioning of the whole. But how does an atom maintain balance with all these particles with different charges? Well, the answer lies in the harmony between protons and electrons. In the bustling city of an atom, protons and electrons are like the citizens, each carrying a charge. Protons have a positive charge, while electrons have a negative one. For an atom to be stable, it needs to have an equal number of protons and electrons. This balance of charges ensures that the atom doesn't have an overall electric charge, keeping the atom neutral. Now, what about the neutrons? Neutrons are like the infrastructure of our atomic city. They don't carry any charge but contribute to the atomic weight. They reside in the nucleus of the atom along with protons and help to hold the nucleus together. Their presence provides stability and prevents the protons from repelling each other due to their like charges. But just like in any city, there can be variations. In the atomic world, these variations are known as isotopes and ions. Isotopes are atoms of the same element that have different numbers of neutrons. They have the same number of protons and electrons, so the overall charge remains balanced, but their atomic weights differ. On the other hand, ions are atoms or molecules that have gained or lost electrons, resulting in an overall positive or negative charge. This imbalance of charges doesn't disrupt the atom's stability, but gives it a new role in chemical reactions. So, you see, each particle in an atom, whether charged or not, plays a crucial role in maintaining the atomic balance. They work together, like citizens in a well-organized city, each playing their part to keep things running smoothly. In the end, it all comes down to balance. Just like a city needs a balance of different roles to function properly, an atom needs a balance of protons, electrons, and neutrons to maintain stability. So like a well-run city, an atom needs balance to function properly. So let's take a step back and look at the atom as a whole. Imagine a bustling city full of life and activity. This city is a metaphorical representation of an atom. The atom, like a city, is composed of various parts, each performing a unique and essential role. In the heart of our city, we have the city center or nucleus bustling with protons and neutrons. Protons, with their positive charge, are like the city's administrators, setting the tone and identity of the city, or in atomic terms, the atomic number. Neutrons, on the other hand, are the city's workers, contributing to the atom's mass but remaining neutral, not swaying the city's charge one way or another. Circling around the city center, like suburbs on the outskirts, are the electron shells. These shells, filled with electrons, are like the residents of the city. Electrons with their negative charge are attracted to the protons in the city center, but each shell or suburb can only hold so many residents. This arrangement of electrons determines how the atom or our city interacts with neighboring cities, or in other words, how atoms form chemical bonds. The stability of the atom, much like the stability of a city, depends on a balance. Too many or too few residents in the suburbs or electrons in the shells can make the city unstable. Likewise, an unbalanced city center with unequal numbers of protons and neutrons can lead to an unstable atom. Understanding these components of an atom and how they work together is like understanding the layout of a city. It lays the foundation for understanding more complex concepts in chemistry and physics, and it helps us understand the natural world around us at a fundamental level. So the next time you look at anything, remember, it's all just a bustling city of atoms.